Okay, welcome to the class. Today we're going to have a look at section 1.6, which is the second part of chapter 1, lesson 3. Going to have a look at relative motion. Well, suppose that you're flying in an airplane at a constant velocity south. Your view from the window might be similar to the view in figure 1a shown here. How would you describe the view? At first, the answer might seem simple, and you would describe the clouds and the ground. After a little thought, you would realize that you can see much more. From the point of view of the plane, the ground and the clouds appear to be moving north, and the plane appears to be stationary. However, from the point of view of an observer on the ground, which is shown here, in figure 1b. The plane is moving south, the ground is stationary, and the clouds are moving with the wind. So the plane scenario illustrated here is an example of the relative motion. The pilot and the passengers in the plane are in one frame of reference or have one point of view. And the observer on the ground is in another frame of reference. So be careful with the concept of frame of reference you choose. A frame of reference is a coordinate system relative to which motion is described or observed. The velocity of an object relative to the specific frame of reference is called the relative velocity. When analyzing relative velocity problems, we will use a vector symbol, vector v, with two subscripts in capital letters. The first subscript represents the moving object, and the second subscript represents the frame of reference. For example, suppose an airplane P is traveling at 450 kilometers per hour north relative to the frame of reference from Earth, which is abbreviated as E. Then the vector VP here vector P is the velocity of the airplane relative to Earth. And we write the relative velocity like this. Vector P equals 450 kilometers per hour. Direction is north. Now suppose we analyze the scenario further to be more realistic. At the altitudes at which airplanes fly, the air, which is abbreviated as A, often moves very fast relative to the ground. So we must also consider the velocity of the plane relative to the air, which is denoted by vector v PA, plane to air. And the velocity of the air relative to the ground, vector AE, meaning velocity of air relative to ground or Earth. In addition to the velocity of the plane relative to the Earth, vector PE. Okay, so the relationship that connect these three relative velocities can be given by vector PE, which is the velocity of plane relative to Earth, equals vector PA, which is velocity of plane relative to air, plus the velocity AE, which means velocity of air relative to Earth. So this equation here applies whether the motion is in 1, 2, or 3 dimensions. Also note that these three quantities are all vectors. So they apply no matter what the dimension is. In 1 dimension, solving the equation is straightforward, right? The number could be positive or negative. For example, if the plane is moving relative to air at VPA equals 450 kilometers per hour north, but the air velocity relative to Earth is given by VAE is 40 kilometers per hour north, which means a tailwind because it comes from the tail, right? Then the velocity of the plane relative to Earth is given by vector PE equals vector PA plus velocity AE. We put all the values in, we have velocity PE, which means velocity of plane relative to ground, is 490 kilometers per hour. Direction is north. So the ground speed increases with a tailwind, right? Which makes sense. What would happen if the wind were a headwind, which means the wind comes from the head of the airplane? The airplane's ground speed would decrease to 410 kilometers per hour. Direction is north. If the magnitude of the wind velocity were the same, right? Also, this is quite intuitive. This also makes sense because airplanes slow down relative to Earth because of headwinds. In 2 dimensions, for example, when there is a crosswind, when the solution is also straightforward but requires more steps, we will work through relative velocity problems in 1 and 2 dimensions in the following example questions. But before we start the following tutorial, make sure you understand the pattern of the subscripts in the equation for relative velocity, okay? So again, let's make a summary of this. In general, the equation takes this form, as shown here. So note here the subscripts AC equals AB plus BC. Be careful with the pattern here, okay? So in the above equation, note that the outside subscripts on the right side of the equation A and C are in the same order as the subscripts at the left side of the equation. And the inside subscripts on the right side of the equation are the same, which is B, right? And furthermore, if we add another frame of reference, the equation then becomes vector AD equals vector AB, then BC, then CD. So note that the first letter on the right side is the first letter on the left side, and the last letter on the right side is the last letter on the left side. Okay, so now let's consider a sample problem which checks your understanding to the relative velocity. Now let's consider tutorial 1. Sample problem 1. Relative motion in 1 dimension. So suppose we have passengers on a cruise ship who are playing shuffleballs, as shown here in figure 2. The shuffleball disk's velocity relative to the ship is 4.2 meters per second. Direction is forward. And the ship is traveling in the same direction as the disk at 4.6 kilometers per hour relative to Earth when the water is stationary. Stationary means at rest. So there are 3 questions you need to consider. First, determine the disk's velocity relative to Earth. Then determine the disk's velocity relative to Earth when the disk is moving in a direction opposite to that of a ship. Next, determine the disk's velocity relative to Earth when the water moving at 1.1 meters per second. Direction is forward. Okay, so I'll give you 5 minutes to solve this question by yourself first. Then we'll have a look at the solution together, okay? You can start now. All right, have you finished? Okay, let's have a look at the solution. Okay, question A. We are given VDS equals 4.2 meters per second, which is the velocity of the disk relative to the ship. Direction is forward. Then velocity ship relative to Earth is 4.6 kilometers per hour. And we need to find what velocity disk relative to Earth, right? So we can use the relative velocity formula VDE equals VDS plus VSE. But first, we need to convert the ship's velocity to meters per second because they are using the different units here. Okay, so velocity of the ship to Earth can be converted to 4.6 times 1,000 meters over 60 times 60 seconds, which is about 1.278 meters per second. And direction is not changed, which is forward. Then velocity of disk relative to Earth is velocity of disk relative to ship plus the velocity of ship to Earth, which equals 4.2 meters per second forward plus 1.278 meters per second forward, which is then 5.5 meters per second forward. Then we can make the statement in question A. Velocity of the disk relative to Earth is 5.5 meters per second. The direction is forward. Any questions? Okay, no questions. Let's have a look at the next one. In question B, we can use the subscripts D for the disk, S for the ship, E for the Earth, and we are given VDS equals 4.2 meters per second, and this time the direction is backward. And velocity of ship to Earth is 4.6 kilometers per hour. Direction is forward, which is 1.278 meters per second forward, which we have already converted to meters per second, right? And we need to find the velocity of disk relative to Earth. Okay, again, we can use the equation for relative velocity. Velocity d equals velocity ds plus velocity se. For the ship's velocity, we can use a value from the part A after converting to meters per second. So VD equals 4.2 meters per second backward plus 1.278 meters per second forward, which means 4.2 meters per second backward minus 1.278 meters per second backward. And the result is 2.9 meters. Direction is backward. So the statement is the velocity of the disk relative to Earth is 2.9 meters per second. The direction is backward. Okay, any questions? All right, if no questions, let's have a look at question C. Okay, this time the given information are VDS equals 4.2 meters per second, direction is forward. VSE is 4.6 meters per hour, which is 1.278 meters per second, direction is forward. And VWE equals 1.1 meters per second, direction is forward, which is the velocity of the water relative to Earth. And then we need to find velocity d. Okay, so this time we have the sum of three velocities, right? Vd equals Vds plus Vsw plus Vwe. And for the ship's velocity, use a value from the part A of converting the meters per second. We have VDE equals 4.2 meters per second forward plus 1.278 meters per second forward, then plus 1.1 meters forward. Then the velocity of the disk relative to Earth is around 6.6 meters per second. Direction is forward. So the velocity of the disk relative to the Earth is 6.6 meters per second forward. Okay, so this is a typical question regarding to the relative motion in one-dimensional case. Do you have any questions? All right, if no questions, let's have a look at another example. So this sample question here is about the relative motion in 2 dimensions, but at right angles. Okay, so we have a boat illustrated in figure 3 is heading due north as it crosses a wide river. The velocity of the boat is 10.0 kilometers per hour relative to the water. The river has a uniform velocity of 5 kilometers per hour due east. Can you determine the boat's velocity relative to the observer on the riverbank? Okay, again, I'll give you 5 minutes to have a look at this question by yourself. Okay, have we finished? Right, let's have a look at the solution together. Okay, so we can use the subscript V for the boat. W stands for the water and E for earth. Then velocity BW equals 10.0 kilometers per hour. Direction is due north. And velocity WE is 5 kilometers per hour. And direction is due east. Then we need to calculate velocity BE, both the magnitude and direction. Okay, so this problem involves vectors in 2 dimensions. So we'll use the components to solve it. The vector form a right-angled triangle. So the solution is straightforward. To determine the magnitude of the velocity of the boat relative to the ground, we can use the Pythagorean theorem. Then we can use the inverse tangent ratio to determine the direction, right? Okay, so in this right triangle, we know the magnitude of VBE equals the square root of the squared magnitude of VBW plus the squared magnitude of the velocity WE. Then put these two values in, we have the magnitude of vector BE is about 11.2. The unit is kilometers per hour. Then we'll find the angle theta here. We know tangent theta is the ratio between the magnitude of VWE and VBW. And again, put all the values in. We have tangent theta is 1/2, which means in the right triangle, theta is approximately 26.6 degrees. So the final statement is the velocity of the ship relative to an observer on the riverbank is 11.2 kilometers per hour, and the direction is 26.6 east of north. Okay, any questions? All right, if you have no questions, let's consider another problem, which is very similar to this one, but given information has been changed. Okay, so let's consider this problem here. The driver of the boat in the previous problem here moves with the same speed of 10 kilometers per hour relative to water, but now wants to arrive across the water at a location that is due north of this present location. The river is flowing east at 5 kilometers per hour. In which direction should he head? And what is the speed of the boat according to an observer on the shore? Okay, be careful. This time, the boat wants to arrive across the water at a location that is due north of its present location. Okay. Okay, again, I'll give you 5 minutes to have a look at this question by yourself, and then we'll have a look at the solution together. What is the heading of the boat, such that the boat can arrive across the water at the location that is due north? All right, let's have a look at the solution. So this problem involves vectors in 2 dimensions, but we do not know the 2 complete vectors, right? So first we'll draw the vectors triangle and then resolve the triangle. You can draw vector BW in the northwest direction as shown here in figure 4, and then add velocity WE head to tail. The sum of these 2 vectors, velocity BE, must be directed due north as shown here, because this is the required velocity of the boat. Then we can determine the heading of the boat using the definition of sine. To calculate the magnitude of the velocity of the boat relative to an observer on shore, we can use the Pythagorean theorem. So first, we can determine the heading of the boat. Sine theta equals the ratio between the magnitude of velocity WE over the magnitude of velocity BW, which is 5/10. And this gives us theta equals 30 degrees in this right triangle. Then we have the magnitude of velocity B is the square root of squared magnitude of velocity BW minus the squared magnitude of velocity WE. Again, this is according to the Pythagorean theorem, right? And then put all the values in. We have the magnitude of velocity B is approximately 8.66 kilometers per hour. Then we can state that the heading of the boat is 30 degrees west of north, and then the speed of the boat relative to the shore is 8.66 kilometers per hour. All right, do you have any questions? Okay, if you don't have any questions, you can take a 10 minutes break, and after that, we'll have a look at the last question of today's lesson. Okay, you can take the break now. All right, welcome back. Let's have a look at another simple sample problem. So this time we have the air velocity of a small plane is 230 kilometers per hour. The direction is 35 degrees east of nose. When the wind is blowing at 75 kilometers per hour and the direction is 25 degrees south of west. Can you determine the velocity of the plane relative to the ground? Okay, again, I'll give you 5 minutes to consider this problem by yourself, and then we'll have a look at the solution together. Right, have you finished? Okay, let's have a look at solutions. So we can draw a diagram to illustrate this question. Diagram is shown on the left. Then we can let vector PA denote the velocity of the plane relative to the air, and let angle alpha be the angle that vector PA or velocity PA makes with the positive x-axis. Then we can let alpha equals 55 degrees according to the given information. And then we know vector or velocity PA can be resolved to two components. X component is 230 times cosine 55 degrees, and the Y component is 230 times sine 55 degrees, which is around 131.9 and 188.4. The unit is kilometers per hour. Then we can do the same thing to resolve vector AG into two components along the horizontal and vertical directions. The vector AG can be resolved to 75 times cosine negative 155 degrees. And the Y component is 75 times sine negative 155 degrees. And this is around negative 67.97 and negative 31.70. Again, the unit is kilometers per hour. Then we can let another vector VPG denote the velocity of the plane relative to the ground. Then, according to the formula, we know vector PG should equal vector PA plus vector AG, right? So put the components of vector PA and vector AG in this formula. That gives us vector PG is 63.93. This is X component. And the Y component is 156.7. Again, the unit is kilometers per hour. Then, if you know the two components of vector PG, we can then find the magnitude of this vector, right? The magnitude of this vector velocity PG is the square root of the squared X component plus the squared Y component. And this gives us approximately 169.2 kilometers per hour. Then we can use a letter theta denote the angle that velocity PG makes with the positive x-axis. So again, note that there are unlimited number of solutions for our theta here, because all of the coterminal angles could be your angle theta. But we do have this relationship. Tangent theta equals 156.7 over the x component, 63.93. This is according to the definition of tangent in the 2D Cartesian plane. And this gives us approximately 2.451, right? Also, we know the x component and the y component are both greater than 0. So we know theta must be in the first quadrant. So one possible solution for theta is arctangent 2.451, which is approximately 67.8 degrees. Then you can denote the direction of the velocity in quadrant bearing. So in quadrant bearing, that should be 22.2 degrees east of nose, right? So the final statement is the velocity of the plane relative to the ground is 169.2 kilometers per hour, and the quadrant bearing is 22.2 east of nose. Okay, so have a look at this question. Do you have any questions? Okay, if you don't have any questions, that's the end of today's lesson. And please remember to complete your homework on Google Classroom and submit them before the deadline, okay? And I'll see you next time.